thank you very much. Thanks to Jerry and to Niall for putting on a wonderful meeting. I think you should be very proud of yourselves. Okay, I'll get straight into it. Optogenetics is a very exciting technique which has been around for about a decade now in the central nervous system. We're about 10 years behind, I think, in the enteric nervous system. Cut a long story short, it's a technique where you extract the DNA from algae and you can implant that DNA, those light-sensitive ion channels, into mammalian tissue. It's a beautiful technique, the guys that thought of it, and it allows us to manipulate the excitability of particular types of cells. This was sort of the original technology in mice. I'm going to show you some wireless technology that we've developed. So you guys, I think, all probably well and truly know that the enteric nervous system is very unique. It's the only internal organ with its own, the GI tract's the only internal organ with its own nervous system. Our strategy, cut a long story short, was to express channel rhodopsin, which is an excitatory fluorescent ion channel, in excitatory neurons in the enteric nervous system, not all the neurons. Okay, so if you are to extract a colon from a mouse, you can record propagating contractions which move along the mouse colon. These sorts of activities occur in every mammal that we've recorded in vitro, including the human colon. So basically what we do, we remove for the first part of the talk, we remove the whole colon from a particular type of mouse, and we can illuminate blue light. Blue light selectively activates channel rhodopsin in the neurons that we're interested in. We have mechanical recordings and we have some electrophysiology from the colon at the same time. I'll very quickly describe the mice that we made. These are not commercial. Cre is an enzyme, and we basically bred two strains of mice together, one with Cre driven by a calretinin promoter, and then we bred them with some AI32 mice which had a yellow fluorescent protein and channel rhodopsin. And cut a long story short, when these two mice are bred together, we will have channel rhodopsin and a yellow fluorescent protein, notionally only in neurons that are excitatory, which express calretinin. We could prove that by looking at the yellow fluorescent protein that co-localized well with calretinin, and the yellow fluorescent protein also co-localized well with cholinergic neurons. This is not really new. This is exactly what you would expect, but it doesn't co-localize well with nitric oxide synthase neurons, which are inhibitory. We dispersed the neurons, and we could patch them and find that in Cre-negative mice, blue light didn't do anything, but we could evoke an inward current and a spike in cells that are Cre-positive expressing channel rhodopsin. That's a purely proof of principle. This is the motility in the colon of mice. This is purely control, and this is the electrophysiology, and these are the propulsive contractions that propagate along the colon. What happens if you illuminate blue light onto mice that express channel rhodopsin and excitatory neurons? I can talk about this for a week without a breath, so it's hard to summarise in 12 minutes. Cut a long story short, as soon as the light is illuminated, you get a polarised reflex, which after quite some latency triggers a motor complex. These events are spontaneous, and this is an evoked event. How do we know that's evoked? Couldn't you argue, oh, that's just spontaneous, maybe that's just like an ectopic heartbeat? You certainly could argue that, and in fact you do find that. So we had to analyse it very rigorously, and I'll show you the analysis in a minute. But basically this is what happens as soon as light is imposed on the gut wall. We trigger a descending relaxation and an ascending contraction. After quite some considerable latency, the circuits converge, and I can explain how this motor complex works and if you want to talk about after, which then propagates along the gut wall. We found that in each animal, the spontaneous variability of the motor complexes, the evoked events, was always outside the 95% confidence limits of the spontaneous variability. What does that mean? It means that when we believe we evoked an event, that was certainly outside the natural spontaneous rhythm. Okay, see if my video works. This is a mouse from calretinin expressing animal. Here's blue light delivered to the colon, triggers a contraction, and the contraction migrates along the gut wall, and we can eject content. If you watch here again closely, right underneath the light source, you'll see the muscle cells contracting directly underneath the light. So this event causes local contraction, and depending on the level of distension and the amount of content in the gut wall will determine how far the motor complex propagates. I think we stimulate it one more time, and you can stimulate all day and the phenomenon won't run down. Okay, if you look at a mouse that doesn't express doesn't express channel rhodopsin, this is the proximal colon up here, you can illuminate with the exact same frequencies and wavelength and nothing will happen. Okay, so this is the motility in a Cre negative mouse. These are the normal natural motor complexes. When we deliver the same stimulus, we don't disrupt the intrinsic rhythm. Okay, this is perhaps the most important slide in the talk. Where are we going with this technology? The ability to control transit without drugs, I think, is the future of our field. Drugs, we heard from Andre very successfully, a lot of the agonists act all over the body. We don't want to stimulate receptors in every other organ system. We want to expel an increased amount of content when we want to without stimulating other receptors. This showed that the percentage of pellets expelled naturally was significantly higher when we stimulated mice that expressed Cre. That told us that we could apply the same stimulus to both mice, and we were more effective at eliminating content in vitro from Cre-expressing mice. Because I've only got 12 minutes, I might not go through all this analysis. We've got an inordinate amount of analysis. This just shows that the site of delivery of the blue light was closer to the site of contraction that was evoked compared to mice that where Cre was not expressed. These motor complexes are purely neurogenic. This is not new. This has been known for many years now. So what happens if you illuminate blue light when the nervous system's paralysed? Not surprisingly, nothing happens. So even in mice that express channel rhodopsin, blue light will fail to eliminate any motility in the presence of a nerve conduction blocker. This is to show that this is the spatial field of the light delivery. We have a 1 millimetre fibre optic. So this is purely in vitro, and I'm going to move into a minute and show you what happens in vivo. Okay, so how do you do this in a live animal or an animal that's not transgenic? This was the early technology. This was pretty clunky, and the animals is what we call tethered. It has to move around with these wires. It's suboptimal. We built this system at Flinders. Everything you see here we made, apart from the cables we purchased. This is a resonant cavity, and basically it emits microwave energy, very similar to that which would occur off your mobile telephone. The animal is placed inside this cavity, and we can illuminate the light, what we use, light-emitting diodes into the animal. I won't go through all the technology. Basically, you have two antennas, and they're separated out of phase by 90 degrees, so you set up a circular polarising field, and the mouse acts as a dielectric resonator. So the microwave energy from the field drives wireless light-emitting diodes. So these are the ones that we make. Here's the receiver. This is proof that we can have multiple LEDs activated simultaneously, and this is what we implant onto the colon wall to trigger motility in vivo. This is proof that the blue light will be emitted from the wireless LED. That's a real photo, and this is when the cavity is turned on. For what it's worth, we can also activate archirhodopsin by using green LEDs. And that's for a different project related to pain pathways. So this is the surgery, and the animal's anaesthetised. It's a sterile environment. Here are the two LEDs implanted onto the proximal colon. This is what it looks like. We use a tissue glue, same as the sort of surgical glue you use in humans for suturing wounds. This is about a month after they were implanted into the colon, and that's the basic geometry of the system. This is the first and only slide I'm going to show of the wireless. We've done N of 3 at the moment. As I speak, these experiments are being done. Cut a long story short, in mice that are acclimatised, which is very important in that cavity, the stress does change the pellet output substantially. In mice that are acclimatised, there's no difference between Cre positive and negative. The most important thing is that over the stimulation protocol time period, we can show that in vivo we can eject significantly more pellets than mice that don't express channel rhodopsin in calretin positive neurons. We're very excited about that technology. I'm going to finish there. I have a lot more to talk about if you would like me to answer.